Before we move on to talk about full wave rectifiers, let's look at an example that uses a half wave rectifier. So for this circuit below, we're told we want to calculate our peak diode current, our peak inverse voltage seen by the diode, and the fraction of the cycle that the diode is conducting. And so the first two things, of course, we talked about in our previous video. This third thing is something new, and we'll see how to do that here in a little bit. We're told while we're solving these things to use our piecewise linear model with a V gamma of 0.6 volts and an RF value of 0. And we have our circuit shown here below. So as always, I would encourage you all to pause the video and try to work this out yourself. As you get stuck or once you finish, come back to the video and compare your answer with the one shown here. So before we get into the problem, let's ask ourselves, what is the purpose of the circuit? So what is this circuit's purpose? What's it doing? Well, we can see that this is pretty much the same circuit that we saw in the previous video. The main difference is that we now have this battery VB attached on the right side. And so if we think about what's happening, remember our diode is only going to allow current to flow from left to right, or in terms of the battery, only from our positive to the minus terminal. So that means that our battery is going to be charging up. So we've essentially created a simple battery charger. And that's because this diode is not going to allow current to flow from the negative to the positive terminal of the battery, which would of course be taking energy from the battery. So we're only putting energy in. Okay, so now let's take a closer look at how we can analyze for our maximum diode current and our peak inverse voltage. So again, this circuit is very similar to what we looked at last time. The main difference is the addition of this battery. So instead of only having to overcome a V gamma, our source voltage, this Vs, now has to overcome the cut-in voltage of our diode, V gamma, and the voltage of the battery. So we can say that when our Vs is greater than our V gamma plus Vb, that's when we're going to have the condition of our diode is on, it's allowing current to flow, our battery is charging. If our Vs is below that value, so V gamma plus Vb, our diode is going to be off. And our battery is not going to be charging. It's going to have zero current running through it. Okay, so of course our maximum diode current is going to correspond to when our diode is on. So let's take a look at that first. As we saw in the previous video, that's going to occur when we have the maximum value of this Vs, which we can get from the magnitude there. So let's go ahead and say ID peak occurs when our Vs is equal to Vs max, which in this case is the magnitude given in our problem up here of 24. So 24 volts is our maximum source voltage. Now, if we want to figure out what our peak diode current is, we can look at this resistor, because we know that that diode current is going from positive to minus, creating a voltage drop like this. So if we want to solve for that diode current, we can use KVL and Ohm's law. So I can say this voltage across the resistor from KVL is equal to the 24 minus VB minus V gamma, and let's turn that into a square, and then divide that voltage by 100 to get our current. So that was a KVL loop. And again, I've substituted because we've said this is V gamma, so I've not shown explicitly that substitution from our piecewise linear model, and I've also just said that this is 24 volts. So let's come down here and put that in terms of an equation. And I know that was kind of fast, so if anybody has any questions about details of that, definitely let me know. So our ID peak is equal to our Vs max minus our Vb minus our V gamma divided by R. So our Vs max we said is 24 volts, our Vb is 12 volts, and our V gamma we're given in the problem statement is 0.6, and we have that our R is 100 ohms. Now, because everything is in terms of volts and ohms, our current is going to be amps, so we have 0.114 if we plug that value in, but of course we can represent that as milliamps as well, 114 milliamps. And so that's a relatively small amount of current, and most diodes are going to be okay with that, but we always want to check the specs to make sure that's the case. Okay, so now our second thing we wanted to find, our peak inverse voltage, is going to occur when our diode is off. And more specifically, it's going to occur when our input voltage, our Vs, is at a minimum. So our peak inverse voltage occurs when Vs equals Vs min, which is negative 24 volts. Okay, so remember our diode is acting like an open circuit, so really quickly we can just redraw this circuit to look something like this. We have our Vs and we have our resistor, which really isn't going to matter because we have no current. So we have 0 volts across our resistor, and this is our Vs min, and this is our Vb. Now I'm going to switch the polarity for our diode because here we have our diode voltage, but if I want to talk about reverse voltage of the diode, I can say that that's positive here and negative on the other side, so V sub R. And of course that's like saying if we have a reverse voltage of negative 9, then our VR is equal to 9. So hopefully that makes sense to everybody, but if not, let me know and I'll try to clear that up. Okay, so now our peak inverse voltage is going to be that VR value when our Vs is Vs min. And now remember what our Vs min means is that that is negative. So if it's negative, we actually have the positive polarity on the bottom and the negative here on top. So we have something that looks like this. And again, the 24 is coming from the magnitude of this input voltage here. So again, we can do a KVL and we can say that this VR is equal to VB plus the 24, and then we have 0 across that resistor. So we can say our peak inverse voltage, which is equal to VR as I've drawn it, is equal to 12 plus 24, which is equal to 36 volts. And so what that tells us is that our diode has to be able to withstand 36 volts in the reverse direction without breaking down in order for this battery charger to work. Okay, so there are our first two items, and we had seen how to do that before, but now for our third item, this is something new. We want to determine the fraction of the cycle that the diode is conducting. And ultimately, we're going to relate that to efficiency of our charger. So in order to get a better idea of sort of what we're doing here, let's come down to a new page and let's look at a plot similar to what we saw in our previous video. So what I have here in the blue curve is our Vs. So this is our source voltage. And I've got my positive 24 and the negative 24 labeled. And then I also have a line here for our Vb plus V gamma. So remember, Vb plus V gamma is the point where our diode is going to begin conducting. So if we were to draw our sort of time when our diode is conducting, we would have something that looks like this. So we would have some voltage across that resistor. We would have current in that battery source during that time. So notice the peak voltage gets up to Vb plus V gamma. And what we want to do, sort of our key times, because again, we're looking at percent of our cycle. So notice I've got this in omega t, our axis here. So this point would be omega t1, and let's randomly call this omega t2. Okay, so again, we can see that this is where our diode turns on, and we know that that value is Vb plus V gamma. Vb is 12, gamma is 0.6, so we have 12.6 volts. So we can say the first instance of turn on, so first instance of diode turning on is when we have Vs equals 24 sine of omega t1. And so we know that's going to occur when that whole thing is equal to 12.6. Well, now what we can do is we can solve for this omega t1. So we can say that the omega t1 is equal to the inverse sine of 12.6 divided by 24. And it turns out that that is approximately 31.7 degrees. Now, what we can say is from symmetry, the distance between omega t1 and this 0 point and omega t1 and this 0 point is the same. And of course, at this middle sort of intersection here, we know that's where our argument of sine is 180. So we can say from symmetry, we have that omega t2 is just equal to 180 degrees minus omega t1. And so that is approximately equal to 148.3 degrees. All right, so now that we know these two distances, we know, well, not two distances, rather, let me come up here. Now that we know the distance between omega t1 and omega t2, we can say, well, that distance divided by 360, which is the distance of a whole cycle, we can get the percent of the time that the cycle that the diode is on. So we can say our percent conducting is going to be 100, to make it a percent, times the difference in those two angles, 148.3 minus 31.7 degrees, divided by the full cycle, which is 360, and we get approximately 32.4%. And so what we notice is that this diode is only conducting about a third of the time, so that's not a very good efficiency for a battery charger. And so this kind of drives home that point that our half-wave rectifiers, although they're simple, are not nearly as efficient as we could be. So we want to find a way to increase this number for our percent conducting in order to not be wasting energy.